Evening, everyone. My name is Mike Flatley. I'm the CEO of the Royal Society of Victoria. I am a disembodied voice for those who are watching via Zoom tonight, but for everyone else, I'm here down at the control desk tonight. Well, welcome. It's lovely to see so many of you in the theatre tonight. Thank you for coming out on a cold winter's Melbourne evening. And it is my honour to introduce you to, if you haven't met him yet, the President of the Royal Society, Mr. Rob Gell, who's going to take us through this evening. Go ahead, Rob.
Thank you very much indeed, Mike, and may I add my welcome to everyone to tonight's proceedings, both here in person at the Royal Society of Victoria's Ellery Theatre, via Zoom webinar and online, live streamed via YouTube to the people online. Before we begin, in the spirit of reconciliation, we acknowledge that all of us are located on the traditional lands of the state's first scientists, the many different First Nations peoples who belong to the diverse lands and waters of what we now call Victoria. We're coming to you tonight from the lands of the Wurundjeri people of the Woiwurrung language group. And I invite everyone joining us tonight, otherwise on tonight's Zoom webinars chat function or via YouTube's comment section, for those following the live stream, to acknowledge the traditional custodians of your own local country, and join me in paying respects to elders past and present. And we likewise extend that respect to any Indigenous Australians who have joined us at the meeting this evening. A very warm welcome to everyone, in particular to our colleagues from the Geological Society of Australia's Victorian Division. It's nice to be amongst geologists. There are many RSV members who are fascinated by geology and who are keen geologists themselves. And of course, this is our annual event, the Howard Lecture, and we run it in conjunction with the Geological Society of Australia's Victorian Division. Tonight, we're delighted to be joined by Professor Andrew McIntosh for his presentation in this year's lecture. Alfred William Howard was a foundational figure at the Royal Society of Victoria. Howard was an early member and counsellor of the Royal Society, known for his capable bushcraft and his role in recovering the only survivor of our society's ill-fated Burke and Wills expedition, John King at Cooper's Creek. We've got some ideas about that, how we might celebrate John King in future years here at the Royal Society. We need a sculpture. Howard was a polymath, driven by his fascination for Victoria's landscape and also its local Indigenous peoples. He pioneered the use in Australia of thin section petrology and the chemical analysis of rocks. His fundamental contribution was the discovery and exploration of the Upper Devonian series north of Bairnsdale. He also made important studies of the Lower Devonian volcanics in East Gippsland and compiled magnificent geological maps of the area. Then also in botany, his 1889 work, The Eucalypts of Gippsland, became a standard authority, and he collected hundreds of varieties of ferns, grasses, acacias, and flowering plants. But his greatest eminence came from his work in anthropology, recording the culture and languages of the peoples of southeastern Australia, particularly the Gunai-Kurnai of Gippsland, which dominated his work from 1872 until his death in 1908. So Andrew is presenting Howard's memorial lecture this year, titled Glaciers and Ice Sheets in a Warming World. Let me tell you a little bit about Andrew, because he has quite a CV, and it's very brief here. Professor Andrew McIntosh is head of the School of Earth, Atmosphere and Environment at Monash University, and is a chief investigator of the Australian Research Council's Special Research Initiative, Securing Antarctica's Environmental Future. His research aims to improve our understanding of glacier and ice sheet response to climate change, including assessing the impacts on sea level, water resources and ecosystems. He's a regular commentator in the media and was a lead author of the IPCC special report on the oceans and cryosphere in changing climate, published in 2019. Andrew's work has taken him to the world's major mountain ranges, as well as the ice sheets of Antarctica and Greenland. He's a PhD from the University of Edinburgh, a postdoc from Utrecht University, and he's held visiting positions at Columbia University and the University of Bristol. Prior to Monash, he was director of the Antarctic Research Centre in Wellington in New Zealand. Welcome, Andrew. Come and have a few words. You stand on this side and I'll stand on that side. I'm fascinated by what you're doing. And you know a little bit about me. I was lucky enough to go to Antarctica in summer of 1987 with a television station. But little did they know, and I was presenting weather on the telly. I think they thought I was going to come back and tell everyone how cold it was in Antarctica. Of course, in fact, we didn't experience a blizzard in 6 weeks. And we had one occasion where we're sitting on Skull and Monolith in our T-shirts, counting Antarctic petrels. But a fascinating place, and it led me to understand a whole lot more about things that I didn't really know I was interested in, but have continued interest ever since. So I'm really looking forward to your presentation tonight. How did you get into Glaciers and ice sheets, or the space you're in, the cryosphere?
I mean, Australia doesn't have any glacier ice, right? So it's the only continent on Earth that's ice-free. So it is a bit of an unusual vocation. Yeah. Actually, I was an undergraduate at the University of Melbourne, and there was a program there that went to Antarctica every year. It was partly the Australian Antarctic Division before they moved to Hobart. But also Chris Wilson, a structural geologist, was based there and took students to Antarctica every year. And actually, Chris is in the audience. So,
Chris, where are you?
Yeah. So at early sort of mentors and inspiration from people around me who were going to this great continent to the south. It's the main reason I got interested. I also just love the mountains and the snow. And I didn't expect, actually, I should have known that you were introducing me tonight. But actually, when I watched TV as a kid, it was pretty unusual for people presenting to the weather to know something about the science. Actually, I always appreciated you.
Still is.
Talking through the details of the weather rather than, what's actually going on rather than here's just the weather. So, these things matter.
Well, I'm very pleased to hear you say that was the objective. Because
it works. Well, I mean, Jane Bunn does the same sort of thing today.
Yeah.
There's a culture of it, but it's important.
Yeah, it's important. It's only, if only we could educate some news directors in commercial television stations, we'd all be a lot better.
Yeah.
We'd all be a lot better. But that sort of brings us back to tonight. So how do you feel about this? I mean, you're working in a critical area. Only in recent IPCC reports, for example, really started thinking about the impact of the melting of land ice and sea level rise and things like that. I still don't think people really get it. So you're now working in a critical space. We've seen our last IPCC report. We've got all the information, the science is in. How do you, when you talk to people say, what do you do, Andrew? They say, oh, I look at ice. What's your response? How are you reading the landscape currently in terms of the work you do and climate?
So when I started working on this subject, this is a photograph of the Drygowski ice tongue in Antarctica and the Ross Sea. It hasn't changed too much, right? So this is not a glacier that's been retreating. It's actually been advancing a little bit. It's in a very cold area. And if you look at it, it's just so beautiful. Yeah, I was kind of drawn to the beauty of these places. Yes. But during my career, there's been so much change in these places. So somehow I need to reconcile this love of beauty and fascination with a system and how it's all working, trying to understand the science as a fascinating and fantastic career, but at the same time deal with the sort of emotional side of seeing so much change. And I do kind of cross this a little bit tonight. Right.
I won't steal your thunder because I was going to say, you've been to Greenland. Greenland frightens me.
Yeah.
When I see things happening on Greenland ice, I say, oh my God, there's an enormous river there that wasn't there when I was born.
So I'm not going to talk too much about Greenland today, but Greenland is 10 times smaller than Antarctica, and it's currently contributing the same amount of water to the oceans and causing the same amount of sea level rise as Antarctica.
I'm not going to sleep.
So it is it's an incredible. It's just like a big mountain glacier that's melting a lot all the way from the top down sometimes. But that's due to, sometimes you get these extreme melt events, and I'll talk about them.
Perhaps there'll be some questions about that, and we'll have some time for questions later. Let's hear your presentation. Thanks for being with us.
Thank you very much. It's such a pleasure to give this lecture. I'm not going to be talking in too much detail about the science. I want to show some photos and some video and give you a bit of a sense of what it's like to be in Antarctica and also to be in the mountains. But I'm going to have to slip some science in as well. So anyway, I'm sure you're all here for slightly different reasons, and I can hopefully talk to the whole audience and engage you in this, what I think is incredibly important subject. Like I was saying, this ice tongue is a place where we've been doing some fieldwork over the last few years, but it was discovered by Scott's party in 1904. If any of you are interested in Antarctic exploration, they called it the barrier because during some of the time, the sea freezes here and it's always frozen on the other side. And it was just this, you going along in your dog sled and get to this ice cliff and have to find a way around it. And it's tens of kilometers long. Anyway, it's a fascinating feature, but it's also got this zigzag, and it makes me think about the kind of threshold type response of glaciers. They're, at one state at one moment, and then they can dramatically change to a different one. I'm going to start in New Zealand, though, where I worked for 17 years. And this is a video, I'll start it in a minute, of the highest part of the Southern Alps. And this is Franz Josef Glacier, which I'm sure most of you know it by this name. But its Maori name, Karoimata o Hine Hukatere, translates as the tears of Hine Hukatere. And Hine was a young woman who loved the mountains. She loved nothing more than climbing the mountains, and her partner, he was afraid of the mountains, and in fact he'd been told that the gods lived there and it was best to keep clear of them. But Hine persisted and convinced Taue, her partner, to go into the mountains with her. And one day they were climbing up high in the Southern Alps, and he slipped and fell to his death. And the story goes that Hine started to cry, and her tears fell down the mountainside and they froze, and they became the Franz Josef Glacier. So here are the tears of Hine Hukatere flowing down the mountain. So in New Zealand, we set up time-lapse cameras to monitor how the ice is changing. So there's a scientific reason for this, but it does evoke these, the tears, and you can see how glaciers flow. It's a viscous, solid flowing down slope, a bit like honey or something. These days, you could feel emotional, cry, perhaps for a different reason, because that's the glacier video there is from 2014, but the photo is one I took from an aircraft this summer in March, and you can see all that ice below is gone, right? So Franz Josef Glacier, like many others, is retreating. And glaciers are retreating all over the world. And this is a Swiss glacier, the Rhone Glacier, very, very well known. And just two photos showing a sort of before and after. And I'm sure for those of you who have an interest in glaciers and you've seen them in the media, you'll have seen plenty of these kind of images. They're from all over the world, every continent. It's a near universal retreat that we've witnessed during the last sort of century or so. You can see this is from 1900 to 2008, but something even more dramatic's happened recently, which I'll talk about soon. And I'm just going to get straight into the guts of this and talk about what's going to happen in the future. And then I'll step back a little bit and talk about some of the processes that are going on, right? But this is a computer model simulation of the glaciers that exist in the sort of central part of the Southern Alps of New Zealand. So for those of you who've been there as a tourist, Franz Josef, you just saw the video, is over here on the western side. Fox Glacier, another famous glacier. This is the Tasman, 25-kilometre long mountain glacier, biggest in New Zealand. Mount Cook Village, for anyone who's stayed. Has anyone been there, stayed in the Hermitage? Or there's a few people in the audience who have been there, right? So this is a computer model of what they look like more or less under today's climate. But under RCP 8.5, this is a climate change scenario that involves no mitigation. It's sort of a burn it all fossil fuel sort of future for our planet. It results in about sort of 5 degrees of warming in the Southern Alps by 2100. And you can see most of the glacier ice is gone in this simulation under a worst case sort of scenario. The bits of ice that are left are either sitting on the highest peaks in the Southern Alps, or there's some debris covered ice that sits in the valley. So Tasman Glacier here is about 600 meters deep. So it's a significant piece of ice. It takes a long time for it to go away, but there's no way a glacier like that can survive. It's dead, and it's just slowly sort of reducing through time. So that's the worst case scenario. But there is a good news story here too, and that's that under RCP 2.6, which roughly equates to a 2-degree warming, it's sort of 1.5 to 2 degrees. I'm sure you hear a lot about this in the media, right? Keeping climate change to 2 degrees or so. above pre-industrial will result in, fewer impacts. And this is an example. So the glaciers have retreated a lot. Let's just go back here. You can see there's considerable change between those two. But at the same time, the ice that's left in the Southern Alps is recognizable. The glaciers are connected to each other. They're still a functioning entity, right? So if we can find a way to keep emissions to a reasonable level and keep in fact, I mean, the detail of this is that actually you need to reduce emissions down to zero. But anyway, let's not get into that. Let's just imagine a future where we can limit global warming to around 2 degrees globally. Then we will save glaciers in many parts of the world relative to today. But we're talking here still, 50% loss rather than 80. Right? That's just a graph showing those two maps that I showed. So it's not great, right? But I still feel like under this scenario, one could travel to New Zealand or any mountain range, and glaciers would still be part of the landscape. They're an important part of our natural, kind of culture, and they're also useful for so many reasons. I'll talk about this in a minute, but keeping climate change under control will result in quite a different outcome. So when Rob was asking a minute ago, how am I grappling with what's happening today, then there is this relatively good news story that you need to keep in mind, that the outcome will depend very much on what we do from this point onwards. All right, anyway, let's globalize a little bit for a minute. Glaciers exist all over the world except for in Australia, like I said before. New Zealand has some, but they're tiny relative to the rest of the world. So the big round circles to the right there show ice volume around the world. This is excluding the ice sheets in Antarctica and Greenland. It's just the mountain glaciers. So you can see the big circle to the bottom in Antarctica, all the mountain glaciers that are disconnected from the main ice sheet, but there's still more ice in Antarctica than anywhere else, even if we're talking about mountain glaciers. But there's significant ice in the Himalayas, in Arctic Canada, in Svalbard and so on. So this is where all the ice is located in the Earth, right? And I'll show you another simulation here. This isn't my work, it's by a colleague from a Swiss glacier, and you can see something similar to what I just showed for New Zealand. We're getting up to the present day now. You see there's been quite a lot of retreat, but in the decades right now, the ice is retreating at a rate that is much greater than even in the last century. And by the end of the century, there's hardly any ice left. That's again under an extreme sort of warming scenario where little climate change mitigation is occurring. And all those big circles around the world, they lock up about 0.5 meter, a bit less, 40 centimeters of sea level equivalent. So if all the glacier ice on Earth was to melt, then sea level would rise by about this much around the whole planet. It's a lot, but it's not, the ice sheets have got much more. I'll talk about the ice sheets in a minute. So under some different warming scenarios, 2.6, where we limit climate change to something reasonable, we get about sort of 4 to 16 centimeters of sea level rise, and it's approximately double that for unmitigated climate change. This is just the glacier component. Right, so glaciers melting cause sea level rise, and the amount that occurs is going to depend on what we do as humans from now on. So I think that for glaciers are really, I think they're very beautiful, they're important, but the main reason I think they're important is for the water security aspects and also mountain hazards, which I'll come on to in a minute. Their sea level contribution is significant, but ultimately the ice sheets will contribute more water to the oceans than glaciers will. So in the Himalayan regions, you can see this image shows Central Asia, the major river basins of Central Asia, the yellow, Yangtze, Brahmaputra, Ganges, and Indus. Each one of them has at least one major megacity at its delta. Right, these are the big cities of the world today, and their water source is the ice towers of the Himalayas. And I'm just going to show you a couple of photos from some of my travels. Right, this is a little glacier on a mountain pass in Tibet, and you can see that there's nothing really. There's a few prayer flags and so on. and a bit of ice up above. But once you get below that ice, especially on the Indus Basin side, so heading towards Pakistan, this is actually in India, but it's the catchment flows into Pakistan, then it's an extremely arid environment. And all of the water comes from the melting ice. And this scales at, from a single little glacier with a little stream that flows down to a mountain village. And there's hundreds of them, and they all combine together into the big rivers of Asia that then feed into, the Indus flows down into Pakistan and it ends at Karachi. I mean, this is the water is for all of these people is coming from the ice. And I'm going to spend a bit of time on this graph because I think it's actually really important. It's trying to illustrate how melting ice is going to change in a future climate. So let's start at the top. You can see there's this sort of bulge, right? And the bulge is how much water is going to come from glaciers, sort of a schematic, so it's not for any particular place. And the idea is that we've got relatively large glaciers today, right? As the climate warms up and they melt, then for a while we'll have even more water. But ultimately those glaciers will recede away and there won't be any water left. So this graph is showing that trajectory through time. And it's called peak water, right? So when the maximum glacier melt's occurring at peak water, it's at this point in the graph, and then it flows off. And seasonally, it does a very interesting thing because during the peak of the summer, during peak water, there's actually more water. So if for regions that are suffering drought during the summer, which of course many places are projected to have increased drought and heat waves under climate change, then for a while, you get some more water to buffer the effects of drought. So again, it's a bit of a good news story, but it's not one that lasts forever. Once the glaciers recede further, peak water's passed and you're in trouble. Right, so this is the sort of idealized expectation of what's going to happen in these places like I was just talking about. And again, we're looking at another map. It might take you a moment just to kind of get your head around what you're looking at here, but this is the UK and Spain. Over here in Asia, the area I was just talking about, these major drainage basins like the Yangtze and the Ganges and so on. The color represents the glacier ice, and it represents the point in time when we think we're going to get peak water. So in the Alps, in the European Alps, the Danube, Rhine, it's gone. We're already past peak water. European glaciers have just retreated so much over the last couple of decades. It's unbelievable. I mean, I've been to places that I visited as a 20-something-year-old, and the ice is just not there anymore, right? But if you go to the Himalayas, to where there's like large glaciers left in the Karakoram, for example, it won't be until the end of this century that we'll reach peak water. So there's a time varying aspect to how water supplies are going to change through time. I think as glaciologists, we've got a few things that we need to do. One of them is to understand what the Antarctic ice sheet's going to do in the next few centuries. I'll be talking about that soon. But the other is an obligation to understand how water supplies are going to change through time for the billions of people that live in this region. Same's true for the Andes, places like Bolivia and Ecuador, and they have similar kind of glaciers in arid environments. If it rains a lot anyway, it doesn't matter. For the places where it's pretty dry and there's ice on the mountains, then this kind of water supply issue is critical. All right, so far I've really just been talking about how glaciers have changed. They were bigger and now they're a bit smaller. But something really interesting has happened just over the last decade or so that's taken me by surprise. And that's rather than just having glaciers that are receding up the mountains, there have been melt events that have been so extensive that they've basically changed the way that glaciers look entirely. And this is a little one we monitored. It's sort of just in from Christchurch, the Rolleston Glacier. And it's how a glacier should look if it's happy, right? So see, it's covered in snow. There's a bit of ice at the bottom, the blue that's sticking out. It's at the end of summer. A glacier like that would remain in equilibrium through time. But this is what's happening during the extreme melt years that we've observed recently. Nearly all the snow's gone. In fact, I'll show you some other places in a moment where everything's gone. There's nothing left but ice. Previous years' snow is removed. So rather than a glacier that's just sort of retreating up the mountain through time, it's having all of its snow stripped off and it's retreating vertically as well as horizontally. And glaciers, they rely on being high in order to attract precipitation and be in a cold environment. So when they get lower, there's a positive feedback and they melt even more. So glaciers thinning are it's not a good thing for their health. So this is another glacier that I was visiting in March. You can see us flying over in a helicopter, contributing to global warming, by the way. You know, it's just all blue ice, right? There's no snow to be seen anywhere. You can see the photo on the right. This glacier is effectively dead. There's still quite a lot of ice there, but there's really no way it can build itself back up again without having what we call an accumulation zone in glaciology. So, yeah, I don't like this extreme melt very much. It has consequences too in terms of impacts. Let's have another look at this. So it's just walking on the ice. This is for fun more than anything. Listen to the sound. Such a brittle sort of thing it's beautiful to walk on. Anyway, so this is the lower part of Brewster Glacier, and we're carrying stakes that were drilled into the ice and measuring how much melt occurs during the summer. And that whole area in front used to be covered in ice, and it's now totally gone. Like, so when I started studying this glacier in 2004, the ice extended right down here to these lakes. And this whole section has disappeared subsequently. And I haven't been there for a while, right? So I turned up there and couldn't believe how much that had changed. So, well, that's not what I wanted to do. Not to, yeah. So between 1900 and 1995, there was a bit of retreat, but the amount of retreat that's occurred since, I mean, actually, it's a bit foreshortened. The distances are about the same, but in 20 years, there's been as much retreat there was in the previous century. It's substantial. So what do I mean by extreme glacier melt in a scientific sense? In Switzerland, they have the best monitored glaciers in the world, unsurprisingly. Everything's perfect in Switzerland, right? And you can see here, each one of these lines on this graph represents an annual measurement of what's called glacier mass balance. It's pretty simple. If mass balance is above zero, the glacier would grow through time. If it's negative, then the glacier would retreat. What you can see in this selection of measurements is that nearly all of them are negative in Switzerland through this period for this particular glacier. And here you can see a sort of distribution. So you get some idea statistically of how we've set, you know, how mass balance has varied through time. But these black lines and this red line sit outside the distribution that we would expect. And, you know, it's one or even two standard deviations outside of the mean in the worst case, right? So for this particular glacier in 2022, there was so much melt that it was basically unprecedented. And the people who do this work couldn't believe how much change had occurred. And up here, you can see the actual change through time. So every year it's negative, right? So it's, you know, normally you'd expect positive and negative, but just negative every single year. But during certain years, and each percentage here represents the amount of volume that's lost from that glacier. So, you know, during whatever it is, 2003, nearly 4% of this glacier was lost. But in 2022, 6.2% of the whole glacier was lost in a single year. And again, as a PhD student back in the late 1990s, I wouldn't have imagined that you could lose that much glacier ice in a single year. So it really does feel unprecedented. I don't use that word lightly. And in 2023, this is a map of Switzerland. You can see, again, the measurements are looking pretty bad, and it's only the beginning of the summer. So each one of these lines on a graph here represents the measurement at the end of summer. So we'll know what's happening in 2023 in a few months from now, September, something like that. Anyway, so extreme glacier melt represents a state of melt that sits outside the expectation from all previous measurements. And so why is this happening? I mean, it's sort of probably obvious, but But we have to understand that as scientists, because you saw a minute ago, the glaciers have retreated since 1900, right? So there was human impact on the climate system in 1900, but not nearly as much as there is now. So how do you disentangle the human and the anthropogenic, the human and the natural drivers of glacier change? It's an important scientific discipline called attribution. And this is Lauren Vargo, one of my former PhD students, now postdoc, who wrote a paper about this for New Zealand glaciers. And the distributions here are just like the ones I showed you, but they've been created in models, because in models you can do different scenarios. The real advantage is you can sort of try an experiment where we just use what are the known natural forces of climate change, solar variability, volcanic eruptions, the sort of things that people like Ian Plimer talk about, but play up and don't understand. I hope he's not in the audience, but these things are real. Climate variability is real. It's an important part of the problem, but the anthropogenic signal is outside of the range of expectation that what you would see from natural variability. And during this particular study, Lauren carried out these two sets of simulations, one with natural variability alone, one with natural variability plus anthropogenic forcing. And you can see that years like 2011 and 2018, which were extreme melt years, sit outside of the distribution of even the ones that are anthropogenically forced. So in other words, for 2018 at Brewster Glacier, the human impact on climate change made this 10 times more likely than if we hadn't had climate change from humans at all, right? So it's not saying that 2018 was due to global warming. It was saying, in a mathematical, probabilistic sense, it's so unlikely that that could have been without human impact, 10 times, less likely. Hopefully that makes sense. Anyway, let's talk a bit about the impacts. So Fox Glacier, it's another one of these, iconic glaciers in New Zealand. And this is a time lapse from 2014. First of all, you can see the mountainside falling down. Yeah, so that's happening because the ice is moving backwards and lowering and debuttressing the slope and causing slope instability. I know this is some people here are probably more geologists than I am, and they want to see things that are more geological. I thought you might like the slope instability aspects. But you can also see the glacier, retreating and breaking up. And I'm actually just going to play this again because it's just so fascinating. There's an impact on tourism here. So when this video started, it was possible to walk onto the glacier and you could do a glacier tour. Has anybody been on one of these at Fox Glacier? Yeah, so quite a few actually, right? Used to be able to just walk up the glacier. But in 2014, the terminus fell apart. You're about to see it collapsing right now. And it made it impossible to walk on the glacier. And in order to do glacier guiding these days, you have to fly by helicopter up to a sort of flatter part further up ice, and then you can walk around. It's still beautiful. It's still, fabulous glacier ice. But I think it's pretty sad that you can't just walk straight on, and it's changed the guiding industry at Fox and Franz Josef as a result. But anyway, it's also just to remind you that as glaciers retreat, the hill slopes are affected, and we're seeing increasing instability in hill slopes all around the world at the moment. It's in the news all the time if you're paying attention. So this is an example. This is not hill slope instability. This is a glacier that just decided to collapse almost instantaneously. This is in the Tian Shan Mountains in Kyrgyzstan last year. A video taken by a British hiker. You've probably seen it. It's had like millions of views on YouTube, right? And people were talking about the avalanche, but this is not a snow avalanche. This is a glacier that was sitting there one moment and then just fell apart the next. And we actually don't understand the processes that could cause this sort of instantaneous ice release, but I bet it's linked to extremes like I was talking about before. So if you haven't seen this already, it's pretty spectacular. Everyone asked, why didn't he run away and why was he busy filming? But, and I stopped it there because it was too big for me to include in this presentation, but actually, he was on the ridgetop and there was nowhere for him to go. And if you haven't seen the video, he ended up just standing behind a rock and the ice avalanche went over the top of him and he survived. Nobody was hurt, but it's an incredible collapse event. And we're seeing these things more and more. And so I'll show it one more time just because it's so amazing. Just from a fluid dynamics point of view, I love this thing. All right, and this is in Austria last week, a mountainside fell down. This one was due more to permafrost melt than glacier retreat, we think, but the summit reduced in elevation by 100 meters in one day, right? So all across the world's mountains, as glacier ice retreats, as permafrost melts, we're seeing these impacts, and they're very serious. And like in Peru, for example, there are some villages that sit at the bottom of streams where you get these glacier lake outburst floods from retreating ice, and they can kill thousands of people because people build their villages on the streams. They rely on the water for agriculture, but then the water is also associated with these extreme hazards. Right, so this is a real issue. All right, I'm switching to Antarctica, and I hope I've got time. The Antarctic ice sheet is larger than Australia. It's a huge feature. On this map on the right, you can see little lines. They're ice flow vectors, where the direction the ice is flowing from. You'll see them moving in a minute. The sort of darker grey areas are ice shelves, which is where the ice is floating over the ocean. They're huge, like the Ross ice shelf, which is just closest to me, the big grey area. It's about the size of France or Spain. It's a floating glacier the size of Spain, right? And it's got an ocean underneath it that's largely unexplored. So people have drilled a few holes through the ice here and there, or sent a bit of a submersible a small distance, but this is largely an unexplored area of Earth. And I'm going to show you how the ice has been changing in Antarctica over the last sort of 20 years or so. And this is using the GRACE satellites. They're orbiting around the Earth. They are a fixed distance, well, no, sorry, that they sit a distance away from each other, and the distance changes depending on the gravity of the signal underneath them. So as they fly over a mountain range, there's more gravity. And anyway, so they sort of move, and they've got these amazing lasers that measure the distance between them, which you can then infer change in the mass beneath. So let's have a look at what's been happening with Antarctica. You can see the ice flow. And in West Antarctica, you can see it's starting to go a bit yellow. It's where mass loss is occurring. Over here in East Antarctica, this is to the south of us here in Australia. You can see there are areas where it's getting a bit red as well. So it's not just West Antarctica that's changing. But over here, this is Pine Island Bay, and it's the area where there's been the most dramatic change in glacier ice. Thwaites Glacier is there. So Thwaites sort of is here, and Pine Island Glacier is here. They're the two glaciers in Antarctica that are talked about the most in the media. Thwaites Glacier is nicknamed the Doomsday Glacier. I wrote an article about it last year, and I called it that, and I got in trouble because people say I shouldn't be talking about doom. It's true. They're just like with mountain glaciers, there are ways of potentially holding this ice at bay with different trajectories of future climate. So it's not all doom and gloom, but still there's certain parts of Antarctica where we're seeing rapid change. Others, like here, the blue parts, where there's been a gain. This is where a glacier just decided to stop about 100 years ago. And so the ice is building up. It's not being drained off in the same manner. It just tells you a bit of a story that the flow of ice in Antarctica is complicated. There's all sorts of interesting processes going on. Over here, there's been an increase in snowfall, which is why there's been an ice gain. So understanding Antarctica is complicated. So glaciers have been causing sea level rise. And this is just a graph to show you the budget of sea level rise from the different components. And the top part here is due to the warming ocean. As the ocean gets warmer, it expands and you get more sea level rise. And the lower part down here is due to ice change. The big grey section is from the little glaciers that cover the whole Earth, the mountain glaciers I've been talking about so far. And down here, you can see the ice sheet contributions. Greenland, bigger than Antarctica, and Antarctica down the bottom, right? So Antarctica is currently the smallest contributor to global sea level rise in terms of the full ice budget. But the Antarctic ice sheet locks up about 60 meters of global sea level equivalent. And if it was all to melt, then it would fundamentally change the face of the Earth, right? So it's currently the smallest, but it's the riskiest. And all the ice sheet contributions here have accelerated since about 2010. And the ice sheet projections of what's going to happen to the ice sheets in the future are the least certain part of this budget, which is why we need to study them more. And I often hear as a climate scientist, we sort of understand, for people who want to mitigate climate change, that we understand climate change. It's just about putting money into, mitigation, solar panels, whatever. But there's a whole field of science here where we don't know enough about the fundamental future of our planet that I think we need to do the science as well. Anyway, these are probably a little bit hard to see, and I apologize for this, but there's a reason for it, right? So the top one is a graph of how temperature will change in the future, depending on what climate change scenario we follow. So the top one, SSP5 8.5, it's like RCP 8.5 that I talked about a minute ago, unmitigated climate change, burn all the fossil fuels. And the SS 1.9 down the bottom is, much more mitigated climate change. Obviously, the warmer it will get, the warmer it gets, how warm it gets will depend on how much fossil fuel we burn, right? And it scales to sea level change. The point of this is to say, it gets warmer, we get more sea level rise, unsurprising. But what is really important here is that there's this dotted line, and let me read it to you. This is from the last IPCC report. Low likelihood, high impact storyline, including ice sheet instability processes. This is basically like, if ice sheets do something that we really don't understand, and it's quite possible, then we could get much more sea level rise than what we currently expect. And if you go to 2,300, I know we'll all be dead. Maybe it doesn't matter, 2,300. I think it matters. Because what we do now will commit the ice sheets to change. They start responding immediately, but it takes them a very long time to actually fully change, fully relax in response to the forcing. And by 2,300, you can get many, many meters of sea level rise. And even here, like sea level rise greater than 15 meters cannot be ruled out with higher emissions by 2,300. 15 meters of sea level rise. Do you know what that means? Like, can you imagine it? In Australia, there's $226 billion of commercial infrastructure that's located within 1.1 meter of sea level rise, current sea level, sorry. And that's it's based on 2008 figures. There's been a lot of inflation since then, especially in the last year or so. There's a huge amount of our infrastructure that's built at the coast. And I don't like these figures too much, to be honest. There's a whole bunch of scientific problems with them, but I'll just put them up here because I think they're useful just to imagine the scenario. But look at Melbourne. The blue areas indicate where we would get inundation. And this is with either 2 or 4 meters of sea level rise, actually huge amounts of sea level rise. And these are meant to be for 2,100. They're meant to take into account the extremes on top of the mean change. I don't think it's well done, but the point I want to make here is that Melbourne is actually relatively robust to sea level rise compared to some other cities. And you probably all know these places. I mean, Ruth Reef, who's in the audience, studies the mangroves up here around Tooradin and on French Island. This is the Barwon River. The sort of estuarine environments around Melbourne are the places at risk. Also true for the Yarra and so on. But relatively speaking, we've got a bit of relief. It's not too bad. There's a whole bunch of processes going on that mitigate sea level rise as well. So it's just not as simple as sea level rises by X and you get a certain amount of inundation. But anyway, just imagine that that's how it works for a moment, and then go to Shanghai, and with 3 meters of sea level rise, Shanghai is just deleted, and it's not a lot. I mean, there's all these sort of coastal delta megacities in Asia and that are at risk in the same manner. Not to mention, low-lying Pacific islands, and there's a whole area of our planet that's at risk of sea level rise in a way that, luckily, we're not quite so much. But we're global citizens. We have to care about this, what's going to happen to the world. Right. So I'm going to talk a bit about ice sheets and why it's hard. Like, why is there such a variation in those IPCC projections? Why does it go right up to the ceiling for 15 meters? So why can't we predict ice sheets? We've only got 40 years of quantitative observations for ice sheets from satellites. It's not very long. Ice sheets, there's ice in Antarctica that is 1 million years old. Right, so with 40 years of observations, it's hard to make predictions about a system that's been in place for such a long period of time. So I've been working a bit on that, extending those records. But the other things are the basal zone, the underneath part of the ice sheet. It's underneath kilometers of ice. and we can't observe it. So there's no way, like from satellites, we can't see through the ice. It's opaque to satellites. You have to fly over it with aircraft using high energy sensors like radar to get an understanding of what lies beneath. It's one of the most inaccessible, unexplored regions on Earth. And the same is true for the oceans that sit underneath the ice shelves, like I was talking about before. And then the ice sheet itself has all these complex interactions, which I was getting at. Remember, I showed that there was an area where the ice stream slowed down and it's been gaining mass. That's an example of an ice sheet interaction that's due to the dynamics of the ice itself. So understanding what these things are going to do in the future is by no means trivial. So I'll show you how we do the reconstruction. I get to have a bit of a break. This is one of my former PhD students, Jamie Stutz. When I was in Wellington, he's going to talk about the way we reconstruct ice sheets. It's just a couple of minutes.
Hello, my name is Jamie Stutz, a scientist in the Antarctic Research Center at Victoria University of Wellington. My team of glacial geologists recently completed fieldwork in Antarctica, investigating the history of the enormous David Glacier. In Antarctica, we collect glacial erratics, which are rocks that were entrained in the David Glacier and were dumped off as it thinned, starting 20,000 years ago. Determining the time since a rock was laid down is an incredible feat of science and takes us from deep space to atomic measurements. Exploding supernovae produce high-energy particles, sending them hurtling through space to constantly bombard the planet Earth. This energy changes the rock's chemistry to produce a cosmogenic isotope called beryllium-10. We know how fast beryllium-10 is produced, so counting beryllium atoms will tell us when the glacier dropped that rock off. In the laboratory, we crush the rocks to sand, dissolve them in acid, and pass that through a fancy chemical filter to isolate beryllium atoms. This story of glacier thinning will help inform projections on the future Antarctic ice sheet. Understanding its future behavior will help society brace for the impact of sea level rise due to ongoing ice melting. As I continue my research, my greatest hope is to contribute to our understanding of the past Antarctic ice sheet, while my fear is that I do not currently have any plans of returning to the field. In a nutshell, geologists live by the saying that the past is the key to the future, and our work on understanding the past Antarctic ice sheet will be key to understanding its future.
This was, he had entered this in a short film competition. He got one of the prizes, but it's great to see how students are able to create these sorts of videos themselves these days, and they're so sophisticated. Anyway, this is an example of the kind of data that we create using the approach that Jamie just described. And this is a fairly simple graph. It just shows time before present over here. So this is 25,000 years ago. And on the y-axis, you can see the thickness of the glacier above the present. And each one of the dots represents an age from a rock that we collected and did that beryllium-10 analysis on. And you can do this in a very sophisticated way, but a very primitive way is just to throw this line through it and show that the response of the glacier in this case was near instantaneous. It was once much thicker, and then in almost no time whatsoever, it thinned to a new state. And sadly for us, this seems to be the way that ice sheets respond to climate change in this stepwise threshold type response. So it's really critical to understand it. If you do the statistics on this properly, on this data set, like Richard Jones did, who led this study, you can see that it took about 400 years for this retreat to occur, and it occurred at about the rate that glaciers are currently lowering in West Antarctica. So this is a paleo study that takes the record of understanding glaciers back 15,000 years, and it shows that what's happening today has happened previously, but from a higher sort of surface height than what we have today. And we've got data like this from a bunch of different places now. Actually, the plot on the left with the big red arrow is modern observations of glacier change. And on the right, there is another one of these reconstructions from geological data that shows the sort of near instantaneous retreat of glacier systems, right? So glaciers have got, there's something about them that makes them go from being there to not being there. And that can happen really quickly. And the reason is that in Antarctica, it has this is what the ice, what the land looks like if you take away all the ice. It's our best estimate of what Antarctica looks like underneath the ice sheet using aircraft-based radar data that's flown over the ice sheet over many years. And what you can see is that there are, in East Antarctica over here, there's large areas where the land is above sea level, right? And glaciers are sitting on that high ground, and they're relatively safe in those situations. But where all the ice is being lost today over here in West Antarctica. The ice is a few kilometers thick, but it's sitting on land that's a few kilometers below sea level, right? And those marine-based glaciers are the ones that are vulnerable and that are having this stepwise sort of retreat. And in East Antarctica at Denman Glacier here, you've got a similar situation. That's the ice velocity, how fast it's flowing, very fast over the ice shelf and over the glacier itself. And underneath, you can see there's this land that's well below sea level. And this little spot here, the Denman Trough, is the lowest point on Earth on land, right? So it's under the ice, but it's kilometers deep. There's this big sort of trench sitting under the present day glacier. So what that means is that as a glacier is retreating backwards, it's getting into deeper and deeper terrain, right? So it's moving backwards, but into a sort of hole. And there's this part of a glacier called the grounding line, which is just in here, the bit where the ice shelf peels off the ocean floor and the ice starts to float. The grounding line's retreating into a hole. And there's a mathematical theory called marine ice sheet instability, which basically posits that a retreating glacier that's going back into a hole like that, once it starts to retreat, is unstoppable until it reaches some new steady state location where it can hold its ground again. And in West Antarctica, I'll go back there, there's no spot for these glaciers to stop. They'll just keep retreating into this big hole until they're fully gone. And some of these glaciers that are retreating a lot today, some scientists think they've already started an unstoppable retreat process right now, which will ultimately result in the loss of the West Antarctic ice sheet. That's a highly contentious sort of point of view within science. And so as glaciologists, we're grappling to try to understand if that's real or not and what really might happen if it's not. You know, it's a big question to try to answer. Is this retreat currently unstoppable? We don't know. Denman Glacier, in East Antarctica here, it locks up almost as much ice as the whole West Antarctic ice sheet, actually. And we're heading there this coming summer to do more work to reconstruct how the ice has changed in the past. But there's a big community of people studying different elements of the Denman Glacier, and hopefully together we'll get a better understanding of its current state, what it might do in the future, and so on. Look, I'm almost there. I'm just going to show you a video of an ice sheet model. This is a projection into the future. So we're about the present day now. And this is under the worst case warming scenario. And it's demonstrating that marine ice sheet instability process I was just talking about, where you can now see West Antarctica disappearing. And you can also see East Antarctica just over here, also starting to retreat in a couple of places. And like I said before, what began in West Antarctica at the coast is propagating inwards, and it ultimately results of the entire loss of the ice sheet. This is one model. It's very crude, to be honest. There's lots of problems with it. But it's an absolute imperative for us to make models like this of the future that we can fully believe in, where we feel like the processes that are occurring in the models represent those in reality. There's so many things for us to learn still until I feel like we've got simulations like this that we fully trust. That will give us the sea level projections that will make us more informed for, you know, do we really need to cut out emissions? Well, here you can see the impacts. Choose yourself. Yeah, have a think about it. Here's the impact. What do you want to do? Right? It can help answer that question as a society. But if you decide, okay, we're just going to go ahead as normal, it gives us the opportunity to think about the engineering that's needed to save the Netherlands, or, you know, these are the questions that we need to face as humanity. So this is my last slide. I moved to Monash 4 years ago, and we started a group. We were lucky, a large group of us in Australia, to set up a special research initiative in Antarctic science called SAFE, Securing Antarctica's Environmental Future. It sits across a whole bunch of different institutions. Monash is the lead institution, and this is just the ice sheet group, right? So there are people studying the impacts on ecosystems, all sorts of, you know, policy, all sorts of really interesting things that matter to thinking about the future of Antarctica. But we've got a great group who are working on these very problems that I've been talking about tonight, and I hope within a few years we'll be able to, you know, contribute and help understand what's going to happen to the glaciers in Antarctica. And I'm also trying to get some work going in the Himalayas too, to help understand what's happening to the water resources there. think that's it for me. Thank you very much.
Andrew, am I being too cynical to think, as there are people who are quite happy to see the Northwest Passage open in the Arctic, that there'll be a number of people very happy to see the West Antarctic ice sheet melt, because they'll be able to mine it a lot easier, which is a discussion. That's how I got involved in the late 70s and early 80s. There'll be questions. And I invite you to think about that. And Duca, one of our Royal Society Council members, is with us tonight. She's going to, what do you call yourself? A mic?
Mike Runner.
Mike Runner. 6,000 years ago, the critical period when they saw a lot of melt in ice, is that what we refer to as the Holocene maximum? And it's a warmer period in the Holocene. Is there a link there?
So the big retreat I was showing is probably just what happened when the glaciers were retreating from the last ice age, and they sort of reached a certain point at a certain time, and they got into a deep trough and had the rapid response. But there is a mid-Holocene high stand in sea level that we've never quite been able to link to what's been happening in Antarctica.
Oh, what's happening with ice?
And so Jacinda O'Connor there is working on exactly that problem, trying to understand what Antarctica might have contributed to sea level rise through the last few thousand years.
All right. You've reminded me, I'm going to about one little anecdote. In my trip in 1987, we are very fortunate to have on our voyage Rhys Jones, from an anthropologist from ANU, not with us any longer. Fascinating man. And as we travelled through Iceberg Alley outside Mawson, I don't know whether you know it, whether it's still referred to as that, Rhys made the comment, and I've written down, there's million-year ice. We're looking at a side of an iceberg. He says, looking about the period of the ascent of man, which is a fascinating thing to think about. So what did we do? We put the rubber ducky over the side, went and collected some of this 220,000-year-old ice and put it in our scotch, because it does wonderful. Because as it melts and the compressed air in the ice expands, it starts zinging around on the top of your scotch, which is a fascinating thing to do. Questions for Andrew? Yeah, start at the front.
Thanks, Duca. Roger Dargill from Monash. Andrew, there's lots of glaciers around the world in retreat, but some are in advance and moving forward, and climate skeptics often point to these and say that's evidence that climate change isn't happening. I think I have an understanding of why they're advancing, but I'd love to hear your expert and almost certainly more correct version of mine.
There are fewer and fewer of them every year. Yeah. Look, there are various reasons why glaciers might advance and sort of buck the trend. I can think of three. One is a regional climate anomaly that's different to the whole Earth. I wrote a paper about New Zealand glaciers because some of them, like Fox and Franz Josef, advanced between 1983 and 2005, advanced by a kilometre or so. Right? It's a significant advance. And we're able to show that just the regional climate variability associated with things like the El Nino Southern Oscillation resulted in a New Zealand cooling while the rest of the world was warming, right? So that's one way. It gets cooler in one spot, but the rest of the world's getting warmer. The second way is that sometimes glaciers have internal instabilities related to their flow mechanisms. It's called surging, and they just advance through an internal mechanism that's got absolutely nothing to do with climate forcing. And the third way is that some glaciers that flow into the sea undergo cycles of advance and retreat that are related to, it's a little bit like the marine ice sheet instability thing. There's the bedrock topography and the ocean forcing and everything kind of combined to create an oscillation. So they can retreat a long way in a deep trough, and actually they've retreated too far and they're now too short for the climate and they advance again. Anyway, you can pick one or two of these and try to make a point of it, but like the IPCC SROC report that I was involved in 2019, it's just so inspiring to see hundreds of the world's leading climate scientists come together and write a consensus report about how things are changing. And the evidence from advancing glaciers is so sort of piecemeal and unimportant relative to the overall trend that I just think it's worth explaining scientifically and then moving on. Yeah.
So do we concur, Roger?
Yeah. That's a good question.
Yeah, another question here.
Yeah, Richard Lovell, thank you. That was amazingly interesting. I noticed somewhere early on, maybe slide 3 or 4, you had a cumulative total ice loss from I can't remember how many years back it went, but there's a radical increase in slope, and then it decreases at about 1950. And then, so if you look at the slope of the rate of ice loss, was really early on. I think it was like slide 5, 4, somewhere. It's a graph. And there's further back.
That one.
Yes, that one there. I think it was that one, but there's an increase in slope, and then it sort of looks like the rate of change is decreasing if you go
in here
from about 1950. Yeah, that's it. So that whole, there's a big drop.
So this bit here.
Well, I didn't mean that. If you go back there and you look at the rate of change prior to that, and then this bit, it looks like there's an acceleration somewhere back around 1940 or 30 or whatever it is. And then it flattens out again, and then it hasn't quite achieved the rate of loss at that time. Is there anything that you know that drove that?
This bit in here, including the last bit, was what I was just talking about. There were these various sort of glacier growth periods through the mid to late 20th century in New Zealand that kind of, so those, for people who went to Franz Josef Glacier for the first time in the late 1970s or so, that was around the time it reached its absolute minimum prior to its more recent retreat. Look, I didn't show a slide about this, but there's been really neat work on the attribution of glacier length changes to both climate variability and climate change over the last century or so. And the human impact on glacier length change only becomes apparent in like a statistical, unambiguous way after about 1980 to 1990. And prior to that, all of the things that cause climate variability were causing glaciers to advance and retreat a little bit. But still, the overall sign here is ice loss, right? So back here, it's just natural variability of one kind or another. In New Zealand, there are a bunch of different atmospheric processes and ocean processes that cause variability. I can talk about them at length if you're really interested, right? but go to another part of the world and it would be a different set of processes that would cause those sorts of fluctuations. But what you see over the whole world is the overall trend of ice loss. Steeped right through the 20th century and then massively faster in the last 20 years or so.
Any questions in the online audience, Mike, at this stage?
Lots of nice comments, but no questions.
Another question from our audience here.
Yeah. Can I just ask, related to the loss in the ice sheets, is a significant amount of the retreat because you're getting warmer water coming in underneath them when they're separated?
Again, like I spend ages talking about these things, but that's exactly why ice sheets are melting in Antarctica. There's surface melt. We've got a PhD student, Dominic Saunderson's working on that surface melt, trying to understand it, but it's a small component relative to the forcing from underneath right now. In Greenland, there's surface melt that's dominant, right? And in a warmer climate, Antarctica will be more like Greenland, but it's not there yet. And the fact that it's ocean forcing that's causing Antarctica to retreat now explains the kind of interesting geographic pattern we see in the retreat, where we know there's a lot of warm water getting under West Antarctica and a few places in East Antarctica, just a few discrete places, and the rest of them are still cold. So absolutely.
Can I ask a question about the potential to lubricate? I was thinking about this about Greenland, but lubricating the surface between the ice and and underlying rocks. What's the current research on that?
I mean, it's a complex field. You're talking about glacier hydrology, and I don't know where to start. So if you melt the ice, the water flows down into the glacier, flows through these things called moulins, like the big, I don't know if you've seen pictures of them. They're scary sort of like water slide tunnels that go from the surface right down to the bottom of the ice sheet. Fall into one of them, you're going to die because they get thinner with depth and the water pressure gets higher. So they're very, very scary features. When all that water gets to the bed, it flows in different ways. If it's distributed in films and small ponds and lakes, then it causes the ice to flow faster because it exerts a pressure upwards. But if it's flowing in big channels, then that pressure doesn't occur. And so what happens when the water gets to the bed of an ice sheet is not clear, and it depends on which situation you're in, and it varies from glacier to glacier. It makes it really complicated. So when you're making these future projections of the Antarctic ice sheet, for example, and I was saying before, I don't really believe them well enough at the moment. One of the reasons is that the hydrology is not well included in ice sheet models at the moment. It needs to be.
I knew I was going to have nightmares tonight, but after this one,
Yeah. But this sort of, I love the sort of sense of the macabre in the, the glacier environment, because, it's also, I just feel like I'm going on a bit here, but like a lot of things emerge from glaciers as well that are like
you emerge from glaciers.
I went to a summer school in the European Alps in the late 1990s, and it was the place where Ötzi the Iceman emerged from a glacier. So 5,000-year-old sort of mummy with a bow and arrow, and anyway.
Okay.
So
that's
yeah.
Okay. Yeah. There's a question at the back. Okay.
Thank you for your presentation, Bob Bagnara. The question that I've actually got is looking at history and the cycle of global warming has been around for quite a while, where we go through these cycles of ice age and global warming. What have we done any research with respect to historical global warming events and how that actually applies to what we're seeing at the moment?
I mean, absolutely. It's a massive field. I mean, paleoclimate is the field that you're describing. In the most recent IPCC report, for example, AR6, there's whole sections of it that are dedicated to understanding the natural variability in climate through geological time leading up to the present day. Actually, there are some analogues from the past that are very helpful in thinking about what might happen in the future. So in Antarctica, for example, we think 125,000 years ago, the West Antarctic ice sheet might have collapsed, right? Through time, there have been different forcings of climate. Solar forcings changed, the orbital forcing that relates to the change in, the Earth's orbit causes the solar radiation to vary across the Earth. It gives us some sort of natural experiments in the past that show us what a warmer climate can do. And like I said before, because we've only got 40 years of observations from ice sheets, it helps us to understand the rapid changes that could occur in the future. So I'm actually deeply fascinated by these geological scale changes in climate and ice sheets, and using the two together to better understand the sensitivity of this extremely complicated system and how it responds to climate change.
So just following up, you mentioned that there was million-year ice in East Antarctica. Is that the oldest ice on the planet?
Yep. So we don't know, but there's currently a couple of expeditions, drilling programs. One of them led by Australians to find the oldest ice on Earth, and the oldest ice core at the moment is about 800,000 years old. And there are some places in Antarctica where the ice is a little bit thicker, and where we think we might go back to about 1 million years.
Okay.
Yeah.
Mike got a question, I think.
Yeah.
Thanks, Jake. Yes, I've got a question from YouTube from a lightning rod. And that is, g'day Rod, question, is there any indication or scenario that might be far faster than any of these calculations? Do we have any worries about tsunami bergs crashing into the sea?
I'm not sure about tsunami bergs. So in that graph that I showed that, 15 meters or so of sea level rise might be possible by 2300, and there was that kind of dotted line showing much faster sea level rise that might be possible. That they really are extreme scenarios. There's one ice sheet model that can create those scenarios, but the processes are not well constrained in that model. We're not sure how realistic it is. So I think we are already taking into account what the extremes might look like. But distinguishing between them is the challenge.
Any other questions? Yes.
Thank you, Juka. Ruth here. We don't often get to hear from a global leader in a field, right, like this one. If you had kind of endless resources, right, what do we need to solve understanding, the ice contribution to sea level rise? I mean, like, where is it more modeling required? Do we need to do better fluid dynamics? Do we need more observations?
It's a nice question for a scientist. You've got limitless resources.
No, it's because the geologists are in the room. That's right.
It's all of those things, Ruth. So glaciology is still a pretty small field. One of my colleagues, Richard Alley, likes to show like his little sort of decrepit office down a hallway at Penn State. And this is the glaciology hub for North America. Yeah. And then he shows like NCAR, this sort of incredible fortress sitting on the hill in Boulder. That's what the atmospheric scientists have. I think that a lot of resource into the physics and the modeling and everything is still required. But Antarctica is one of the most unobserved places on the planet. So those observations are critical as well. And we don't know. So we have an idea of what the shape of the bed is like under Antarctica. We don't know what the substrate's made of in many cases. It's soft sediment. It's hard to get at what's really underneath the ice. The ocean processes that are causing that melt are poorly understood. And you've got these giant areas, the size of France or whatever, unobserved. It's modeled, but how good are the models? It's such a big problem. So the answer, I'm sorry to say, is all of it. Yeah.
More money required. Is there another question? Yes, we are.
Just a quick one, if I may. Sorry. I was under the impression that as the ice melted and the weight went off, that the land underneath, in some cases, can start to rise. Do you have any modelling that allows the factors that component in on the stability of the remaining glacier section?
It's a really important feedback, and it's one of the good ones. It causes relative sea level fall next to the glacier, so it can help to stabilize a retreating ice margin. So it has the potential to slow the retreat once it initiates. And it is included in some models, but I don't think it's comprehensively included as a process in future ice sheet simulations. It needs to be. So at the moment, there's a group of us who are trying to build a sort of comprehensive ice sheet model within Australia's climate simulator access. And the important part, one of the important contributors there has to be the response of the crust to changing weight like that.
Is that still called isostatic readjustment?
It is a glacio-isostatic.
Glacio-isostatic. Yeah, I've retained something. I was actually musing before you mentioned erratic blocks in the glacier, and I recall a second-year lecture where the spoonerism, of course, is erotic blacks, which was used intentionally or otherwise. I don't know. Have you ever slipped up?
No, not that one.
Not that one. Is there another question? Yep.
I'm going to pose something a little bit left field here. Would you say, I'm probably a part believer in this. I don't like to be, but I am. Would you say, or what would you say to a comment that we're in runaway mode? And by that, I mean, if you take Australia and some of the countries like ourselves, we can do as much as we like, but you've got some major contributors around the globe that are still producing quite a lot of carbon. If you take all that into account, how would you describe the situation that we're in at the moment?
I mean, it's a great question. It's a really important one, but it's a question for somebody else, to be honest. Like I can speculate as a person, but as a scientist, this is not my field. You're talking about social science, political science, a whole process that, geopolitics. Ask me what the ice sheet might do in response to that, and I can give you a reasonable answer. The rest of it is a question for all of you in a way, right? What do we want to commit to as a society? And you kind of, got at the point that perhaps we're relatively small and there are some big players that it doesn't matter what we do, but we also have the chance to set an example. And I mean, I used to live in a much smaller country in New Zealand, which did take that approach. We're a small country, but we're going to set an example and the rest of the world can follow. I always found that pretty inspiring. Anyway, so I'm not quite answering your question because I think it's not one for me in terms of my expertise.
Andrew's done a good job. If there's not another question, is there a burning question? Okay, there's not. In which case, I'm going to invite Anne-Marie Tossolini, who is the new president of the Geological Society of Australia Victorian Division, to pass a vote of thanks. Welcome, Anne-Marie.
Where do you want me to stand?
So thank you, Andrew, for a fascinating talk. It was very visual and really inspiring, but also a bit alarming. And I think that it's great to have a geologist who is working on the cryosphere at that nexus between the lithosphere and the atmosphere. So I'd like to give our vote of thanks on behalf of the Royal Society of Victoria and the Geological Society of Australia Victoria Division. Thank you to Andrew.
We're inviting everybody downstairs, something, Mike.
That is correct. Supper.
Yes,
is awaiting.
please join us downstairs for some refreshments.
And
thanks for being with us.
And for those watching on Zoom and YouTube, thank you also for being with us. And